Hi guys. Alright, this week we have an online lecture as I told you within the lecture hours last week, since our lecture is cancelled due to a national holiday. So let's start our lecture of week 13, and I really would love it if you guys can listen to this video before our lecture for week 14, which will be our last lecture. So I want to go over quickly what we did on magnetic fields. These mysterious fields were created by moving charges. So currents carrying wires created magnetic fields. Also permanent magnets created magnetic fields. And the reason for permanent magnets to exist was the motion of charges, and specifically electrons, in the atomic level rather than running in a current. And Minute Physics in YouTube have a beautiful video explaining magnets. I'll send you a link, and maybe if you want a reminder of how it worked, you could check that video. So magnetic field inside a magnet goes from the south pole towards the north pole. But the north pole of a magnet is labeled the north pole because magnetic field lines go out from a north pole and go into a south pole, and that's how you know the south end of a magnet. And as you can see, magnetic field lines always form closure. If you put two north poles of a magnet two magnets close by, as you can see, the field lines are clashing. The magnets will feel a repulsive force, whereas if you have two opposite poles, the field lines are kind of hugging each other. These magnets will be attracting each other. Magnetic forces can act on moving charges. We call that a Lorentz force. And the formula is QV cross B. So the charge is important. And if it's an electron, this is the negative charge, and you have to put it in the equation. Cross product, B field it is in. So if this plus particle entered this B field along the same direction with no angle in between, there would be no force. This cross product is there to tell us that. There has to be a slight angle between V and B. How does this particle go? Well, the resultant vector in a cross product is always going to be perpendicular to the other two vectors. So F will always be perpendicular to B and V at the same time. So since it's always perpendicular to the velocity vector, so as this guy goes, it will bend, this perpendicular force will bend its path. But as it does that, the force will also keep changing its direction, so it's going to make this particle go in a circular path. And when the particle is, let's say, here, the force vector is still perpendicular to the velocity vector. So this Lorentz force, which involves in this calculation the angle between V and B, sine theta is there when you're calculating the magnitude. This force only acts on moving charges, and they have to enter a field with an angle. It is always perpendicular to the direction of motion, hence it only changes the direction of motion, giving it a circular path. It never accelerates or decelerates particles. All right, perfect. So when electrons are running in a current with their drift speed Vd, their charges being E, they will feel a force, and they will kind of bend and collect on this upper end of the wire. And when there are a number of these electrons affected by the fields, there will be a net force F total on the wire that will bend the wire eventually, and its magnitude is IL cross B. Here L is a vector that has the direction of current, that's towards the direction of current. Here, in this case, it's going to be towards right. And this L is the portion of the wire that is inside the magnetic field. So if this wire extended all the way out till here, we would not include in our calculations the parts that are not inside the magnetic field. So I gave you guys homework questions regarding these two forces, and I'm hoping you solve them. If you still haven't attempted homework from week 12, please do so. We learned how to calculate magnetic fields. And I gave you guys two methods to do that. One was Biot-Savart law, the other one was Ampere's law. Biot-Savart law really is like how we calculated electric fields using a charge distribution, picking a small dq on a big charge distribution and integrating it, k dq over r squared. Similarly, in Biot-Savart law, you pick a little segment of the wire that carries the current. We call that a ds. We calculate its little magnetic field at point of interest, let's say this point P. We calculate dB. And as you can see, the formula for dB involves angle between this ds and r hat. R hat just being a unit vector, it's only one. It's the magnitude is one. Its direction is important. So different than calculating electric fields, angle between r and ds is actually in the equation. So a sine theta, this theta, a sine theta will come into the equation here. Other than that, it's just like k, magnetic constant. IDS can be dq over r squared, except that there's a sine theta. Remember when we were calculating electric fields, we were using the total flux through a closed surface, Gauss's law, to solve the problems without dealing with too complicated integrals. For that, we had to define a surface, an imaginary surface called Gaussian surface. Here, similarly, we have Ampere's law. This Ampere's law involves not a flux, but it involves a path integral. B along a path. If you calculate B dot ds path integral along a closed path, that's what it means, this circle, it's a closed path, then B dot ds will be equal to whatever B field you may have, whatever path you may pick, it will always be equal to mu0 constant times current that passes through that loop. For example, for this loop number 1, which is a circle, current I passes through it, so this B dot ds through loop 1 will be mu0 times I. But however, if you pick, let's say, the second loop to calculate the magnetic field inside a wire, inside this conducting place, right? Then we would have to include mu0 times I in defined as the current passing through this circle limited by path number 2. For that, we would have to use current distribution J, which is I over A, the cross-sectional area. So when we were calculating magnetic field of a long straight wire, we could do that with two methods. One using Biot-Savart law, which gave us a dB here at this point that was towards out of the page. And for whichever ds we picked on the wire, we got a dB along the same direction. So we could easily do an integral without having to deal with components, which led us to a result b equals mu0 I over 2 pi a being the distance from the wire. We could use this result in our calculations. We can use this general result. We did the same using Ampere's law. We picked a circular path around the wire, and on that circular path, b dot ds integral was just b times 2 pi a, because b followed the circle around the wire. We needed that information to do this calculation. So we actually used the result that we found here, because the result told us here that if you have a long straight wire, B field makes a circle around it. So your B field lines are going in circles around the straight wire. You could actually use your right hand to find the direction. You put your thumb towards current direction. Your fingers will curl, showing the direction of the B field around the wire. So we use that information to calculate this using Ampere's law, because that told us that we could conveniently pick a circular path on which B would be constant, uniform, So that helped us calculate the B fields on that loop, which was mu0I over 2 pi a. So we could generalize it with the right-hand rule, and this is actually how it looks in 3 dimensions. You have a wire, and these are your B field lines making circles around. So picking the right method is important. Ampere's law will not always work for every kind of geometry. For example, this ring. For us to be able to use Ampere's law for this ring to calculate the magnetic field of this ring, we would actually have to know what the shape of these field lines look like. We should be able to name it something like a circle, an ellipse, a square, or a rectangle. It should be something that we can calculate easily, so we can use Ampere's law to predict the B field created by this ring. Since we cannot do that here because these paths have arbitrary shapes, Ampere's law is not a good method for the ring example. So for any curved wire or the ring, Biot-Savart law is a good choice, is a better choice rather than Ampere's law. But here is one example where we can use Ampere's law. Okay, magnetic field of a solenoid. Well, a solenoid is basically a coil. It's a wire wrapped up around the cylinder. And when current passes through these wires, so it's like you have, as if you have many rings on top of one another, it creates a magnetic field in the inside that depends on the current direction, obviously, but it's almost kind of along the direction of the cylinder's long axis and almost uniform. In a non-ideal case, you may get some field lines outside the coil, but if you have these wires very densely packed, if you have 100, 200 turns in a, let's say, 5 centimeter coil, then you have an almost ideal solenoid which creates no magnetic field outside, it's zero, and you only get, this is like a cross section, you cut this in half, it's a cross section of this solenoid, but since they are densely packed, you get almost a uniform magnetic field in the inside. So let's calculate this magnetic field. Let's do that calculation right now. I uploaded lecture note templates, so if you haven't printed them already, you might pause the video and go ahead and print lecture note templates for week 13 if you wanted to fill them out, or you could just simply take notes. So from now on, these are new notes. Please pay attention. So we want to calculate the magnetic field inside a solenoid. And when we want to do that, we have to be given a certain information. We have to be given the total number of turns and the total length of the solenoid. Or we should be given an n number of turns per unit length. Here in this question, we are given the number of turns, small n, per unit length. To solve this question, we need to know what the B field lines are going to be looking like. And as we just argued, the B field lines are almost uniform in the inside, going straight up in this case. These dots show that the current is going in on this end of the wire. So it's like we're looking at half of the coil here. So this wire goes and current comes out. Sorry, I said it the other way around. So current goes in this way, goes through the wire, comes out this way, and it's like we have many of these wires. We're looking at a cross section. Okay. So when these wires are densely packed, and you don't have too much of a diameter here for this coil, what happens outside is that this wire carrying a current going into the page creates a magnetic field on this side that is towards this direction. This wire that carries a current that is coming out of the page, a magnetic field, if we use our right hand rule, that is towards this other direction. So one creates a B field clockwise, the other one creates a B field that is counterclockwise. And these field lines actually cancel each other out in this outer region. And in the inside, this is creating a B field that goes again this way. And this is creating a B field that goes that way. So these little B field lines add up in the inside, forming these straight lines. So Ampere's law is a good choice to solve this problem. If you wanted to pick little DS's on all of these wires and try to calculate the total magnetic field at the center, we would really have to deal with very heavy integration and a lot of vectors, vector components. But Ampere's law really suits this problem because we can pick a path here. And this path can follow the B field because we know that B field is straight at the center. We know that B field is 0 out here in this outer region, so we can easily pick a rectangular path or pick a square if you wish. Okay. For an Amperian loop, so this is our Amperian loop, and work our integral that way. Use our Ampere's law to calculate this B field at the inside. I enclosed or I. Okay, so here's our Ampere's law. It requires a path, and here is our path, or a loop. Here is our loop. But our loop has 1, 2, 3, 4 segments, 4 parts of the loop, since it's a rectangle. So we'll divide this path integral into 4 parts. We'll do b dot ds for path 1. We'll do b dot ds for path 2, and so on. All right. So for number 3, we said that the B field out here will be 0. So this is simply 0. For number 2 and number 4, this integration b dot ds will bring us a b times ds times cosine of the angle in between. So for path number 2, this is b and this is ds. And as you can see, the angle in between is 90 degrees. So for path number 2, we have b times ds times cosine of 90 degrees. And for number 4, we have the same thing. We have b times ds times cosine of 90 degrees. In here as well. So for path number 1, we have the B field going up. So this is our B field. And this is our ds. They have 0 degree angle in between, so we have here b times ds times cosine of 0. All right, so we have everything covered, all parts of the integral. So b dot d is closed loop path integral. 0 here for 90 degrees because of 90 degrees, 0 here because of 90 degrees, 0 here because the field is 0. So b dot ds integral is actually just this term. Cosine of 0 is 1. This is b times ds. And ds, b is the same everywhere on our path. We can just call this as b times the length L. Okay. Equals mu 0 I enclosed. We're almost done with the problem. As soon as we determine what I enclosed is, I enclosed here is what? All of these wires, 1, 2, 3, 4, 5, 6, 6 eyes in this case. But we have to write it in a general form. The question tells us that this solenoid has n number of turns per unit length. We have a total loop length of L that covers the wires. So we have L times the small n. Okay? We have this many wires, and each one of these is carrying a total current I. So we have an enclosed current of L times small n times I. This will give us, this is number of turns per unit length. We'll cancel out with the length. So we're going to have some capital N number of wires carrying current I. So V times L equals L times N times I times mu 0. This gives us a V field. L's cancel. That is mu 0 and I. So we can comfortably use this formula in general. Okay? Magnetic field of a solenoid is mu 0 and I. If we did not use number of turns per unit length, we could have expressed it this way. Magnetic field of a solenoid equals mu 0 times total number of turns divided by the length of the solenoid times I. This is also an option. Replacing capital N, small n with capital N over L. So here is magnetic field of a solenoid. If you wanted to use your right hand to find the direction, you could do that. For example, here's a solenoid looking from the side. Here, current is going downwards this way, going up through the bag, down here. So you curl the fingers on your right hand, showing the direction of the current. Curl them like how this current curls. The direction of your thumb will show the B field inside the solenoid. Ignore this I induced, it's not going to be there. So here is the B field in the solenoid. So finally, we have the toroid. Toroid is like a donut-shaped magnet. So you kind of have this donut and you wrap a coil around it. And let's say this toroid has a total number of turns n. How do we calculate the magnetic field inside this toroid? Well, let's look at the cross section. Let's cut the toroid in half, like here. Cut it in half and look at this cross section. Okay, so we have current running in this outer wires coming out of the page. Current goes around, goes into the page in the inner wires. So let's use Ampere's law again to do that. Here's our Ampere's law. E dot Ks equals mu 0 I enclosed, or In. Now, how does the magnetic field look in the inside? Well, I drew these magnetic field lines with red, sorry, not red, green. However, we could guess how they would look like. Like, if we use our right hand to find the magnetic field created by this little guy, okay, it will make a circle around this one. This, here on this side, current is going into the page, creates the magnetic field towards this direction. And all of these little guys will create magnetic field lines the same way. Again, the same way. So as you can see, all these magnetic field lines will add up to form a circle in the inside of the toroid. That will be the overall effect. So we can pick a circular loop for our Amperian loop. In this case, this red or orange path. Let's give it a radius r. So we can easily calculate its path integral, okay, b dot ds. So on this loop, b dot ds, assuming b is uniform on that path, will be b times 2 pi r, the length of the path. Okay. B in this case will not be uniform in the inside, but since there's circular symmetry, we know that at least it's going to form a circle. And on that circle, everywhere on that circle is going to be the same, because this part on this circle is no different than this part on the circle, is no different than this part on the circle. So everywhere on the circular path, B will be the same value. So B times 2 pi r equals mu 0 I in. And I in means currents passing through this red loop. And I'm looking at it, all these cross-marked wires are passing through the loop. These guys are not passing through the loop. And they all have the same direction. Okay? They're passing through the loop, going into the page. And how many of these do I have? Well, I have n turns in the toroid. So we have b times 2 pi r equals mu 0 times n of these currents, n times I. And here we have it. Magnetic field inside the toroid, mu 0 n times I divided by 2 pi r. Yay! Here we have a general formula. And as you see here, if you get closer to the wires that are in the center, you get a bigger magnetic field. You go outer towards this side, you get smaller magnetic field. So magnetic field is not uniform along the radius, but it's uniform on the circle inside. All right, so that wraps up calculation of magnetic fields.